All right, cool. Hi, everyone. Hopefully you've had a good week and you've had a chance to check out those example contracts as well. So today is, actually, first we'll start with this little piece of news. So I talked last week about the London Ethereum upgrade. So this is the upgrade that changes kind of how gas works. It has a few minor changes as well. And last week it had been successfully deployed to the Ropsten test network. So that's this test net here that we've been using for our kind of local development, and it all went smoothly there. So this week it has gone live on another test net called Goalie, or Goalie, I'm not really sure how to pronounce it. And that seems to have all gone well. So it will also be deployed on these two test nets, so Coven and Rinkeby. We have a lot of different Ethereum test nets. But now that everything seems to be going smoothly, it should be an Ethereum mainnet in the next week or two, hopefully. So we can start playing around with that, which is great. So today, what I wanted to do was finish off some of the stuff we were talking about last week. So we talked about contracts calling other contracts and how we can start to have interactions between multiple contracts on the blockchain. So we'll talk a little bit more about how that kind of works under the hood and what's really going on behind the scenes of the Solidity compiler. Then we'll talk about a specific standard that is used to allow contracts to know what is supported by another contract. Right? So you have a way to actually ask an existing contract whether it is a token or whether it supports an auction and things like that. Then we will start talking more about the different features of Remix that kind of help us build larger scale applications. So things like how the debugger works, how we can use the static analysis tool, how we can use the optimizer, how we can write tests and that sort of thing. And we'll also talk a little bit more about events. So we've seen events in the past as a way of logging information from our smart contract. So we logged when the auction ended or when a highest bid was created. And so we'll talk a little bit more about events today. And we'll finish off with, I guess, our first kind of take-home assignment. So I've got the interface of contract and the description of how it will work. And your assignment will then be really simply to kind of implement this contract, and then we'll all get back together and kind of discuss your implementations, review it, see what we did well and what we didn't do well, and kind of give feedback that way. So a lot of different things to cover.
Okay.
As always, interrupt me if you've got a question or put it in the chat, which I'll keep open. 1 second, just rearranging my windows. Okay, so we're back to Trusty Remix. And last week we kind of talked about contracts interacting with contracts. So going from a single smart contract application to starting to build out applications that use multiple contracts that all kind of know how to interact with each other. You know, one might be a token that we use to make payments. The other might be an auction that actually uses that token to make the final bid. And then you might have, say, a governance contract, which lets you vote on different rules for the auction and things like that. And so by allowing all these contracts to talk together, we can make really kind of small, simple contracts that are easy to test, easy to understand, and then combine them to create bigger applications and do really interesting things. And if we look at, say, the code for the Maker DAI token, so this is the stablecoin that we're talking about, the decentralized stablecoin. We'll just have a quick look at their GitHub. And if I look at there you have a lot of, let's go up here. So for a selective, here we go, DAI stablecoin system. So in this kind of decentralized stablecoin, the DAI one, they actually have all of these different contracts, which if we look at like an individual one, it's not actually that long, 200 lines, right? But these are all deployed kind of together to form a complex system. That's all of these things will kind of perform different, really small tasks. And then when you're doing things like formally verifying your contracts, so mathematically proving that they follow the rules that you've set out so that they're bug-free, you can kind of prove that. These really small contracts make it easy to do that testing, and then you can still build the larger system. So being able to have contracts interacting with each other is kind of a fundamental principle of Ethereum development. So I believe the example we used last week was it share cache? No, it was split my bill. Right, so we had this split my bill contract, and it takes in the address of a token. And this is another token, any token that implements that Erc20 interface. And then it uses that to split a bill at a restaurant. Right, so it's a pretty straightforward contract. Now, because we were the people who wrote this contract, we kind of had the benefit of knowing that our token contract, so this address that we pass in, is an address of something that implements this Erc20 interface. So if I were to deploy this contract, I'll just compile it. First deploy CableCoin with 1,000 coins. This is all very straightforward by now. And then I'm going to deploy split my bill, and we'll pay out to my address. We're going to split a bill of $200. We're going to split it between me and the next person. And the token we're going to use, I can put in CableCoin. Right, and that's how we did it last week, and that all works correctly. But once this contract goes onto the chain, all of this kind of type information, so this IERC20 type, for example, is stripped out. The Ethereum virtual machine doesn't understand that this address here has to make this interface. It kind of blindly does what the compiler has allowed it to do because we specified this type. So when we passed in the address of an actual token that did make this interface, that was all fine and it worked correctly because we had this transfer from kind of function. But I could also just pass in any random address to this contract. So I could pass in, say, an account, right? This isn't a contract. It doesn't meet the Erc20 interface, but I can still pass it in and I can successfully deploy that contract. See here. So I've now got to split my bill contract, but the actual token address here is not a coin. So when our contract goes to try and call the transfer from function on the token, it's now pointing to the address of something that's not a token, and we'll see that this should fail. So if I call split now, we can see we've got a reversion here. And the issue here is that it's tried to access some sort of transfer from function on the address, but it doesn't actually implement that interface. So there is something we can do about this. Now, it firstly kind of requires understanding a little bit about how functions are actually called behind the scenes. So when we're writing our own Solidity code and we know the types of the addresses that we're passing in, like this, it's actually super easy. You just type in the actual function name. But in order to call this function in another contract within the Ethereum virtual machine, it's a little bit more complicated. So what I'm going to do is I'll create a new contract to illustrate this. I'm going to call this one, say, function 6. Okay. So to call a function, what we're really saying is that we want to kind of access it by a name, right? Which might be, in this case, let's make a really, really simple contract. So let's go function. We'll go caps lock on. Cool. So this contract only has one function, and all it does is take in a number and return that number to you. So it's super easy. Now, when we're calling this function name, what's happening behind the scenes is that we kind of take the name of the function, then we take all of the arguments of the function. So in this case, just X, and we look up the function in what's called like a selector table or a function table. So our contract at the start has a big list of function names and then where that function starts in the code, right? So it might look like echo starts at line 5. And what's another function we use, like new bid starts at line 50, right? That's not how it actually looks in memory. That's a simplified view. And then you come into the contract. The first thing you do is enter this kind of function table. We'll look up based on the function we've called where the code starts. Then we'll jump to that line, so line 5, and we'll start executing the echo function. That's pretty straightforward. Now, the way it actually kind of works behind the scene is that rather than using these full names, which obviously can be super long, so you might call this echo, and just repeat that like this, right? Which would just make the function, the call super large. And it also means you can't look up a function using a kind of single small selector. You have to pass in a huge string, and it would just use a lot of computational time. So what we do instead is each of these functions has a selector. A selector is 4 bytes. So it's 32 bits in total. It might look like 4F, right? And the selector is equivalent to this function name. So if echo is 4F, for example, new bid is 85FB in hex, right? And then instead of linking directly to a line number, it links to the instruction number in the list. Because remember, the Solidity code gets compiled down into Ethereum EVM instructions. So it might look like the 80th instruction. Right? So the table would really look like something like this. Right? Now, to get this selector, so the echo selector, for example, it's a kind of standardized process. And what you need to do is you kind of grab the function name and all its arguments. You go to your hash tool, you paste it in, you remove any variable names. So you're left with kind of this. And all you've got is essentially the function name and then all the different types of arguments it takes. So if it took 3 different numbers, this would look like this. You strip out all the spaces and things like this, and you do a hash of it. You get back this kind of long string. And then you take the first 4 bytes. So 2 BBE. This is then the selector for this echo function. One of the kind of cool things about doing selectors this way is that if someone were to call with the wrong number of arguments, so they might only pass in 2 UNs, that makes a different selector, so it won't actually be able to find the function that's been incorrectly called. So we've got this 2 BBE selector. We can then use it to look up echo because the echo table would look like that, right? So behind the scenes, when I was using split my bill, all that actually happens is that Solidity will calculate during the compilation process what the selector for transfer from is. So transfer from might be 0x55BB, right? It will then go to the address of the token and it will look up the function with selector 0x55BB. Because we know that the address has that function, that's fine and it works. But when I passed in the address that wasn't a contract, that didn't implement that function, this lookup failed and the whole transaction reverted. So what would be really cool is if we had a way for our contract to actually be able to check first whether the contract really does support the Erc20 interface when we deploy the contract. So rather than being able to deploy it with any address and it then kind of failing when we try and use it, we should just not be able to deploy until we pass in an address that meets this interface. And this is a problem that a lot of people kind of faced, and the community got together, and just like they came up with a standard for tokens, this ERC20 interface and the ERC721 interface for the non-fungible tokens, they also came up with a different, standard called ERC165. And the way that works is, look here, ERC165, it's an Ethereum improvement proposal like the other ones we've looked at. And this is an interface detection standard. So this standard essentially lets us query a contract while it's already been deployed. So you don't need any information about the contract. You don't need to know who wrote it or what the code was that eventually ended up being compiled down and deployed. But you can still query that contract and see what methods it supports. So you can ask the contract, do you have a transfer from method? If not, then you can fail the deployment, something like that, where you can recover from the error in another way. And the simple summary says exactly that, right? Create a standard method to publish and detect what interfaces a smart contract implements. So this is the actual ERC165 standard itself. It's super simple. We just have this supports interface function that our contract has to implement. It will take in an interface ID, and then it will return true if it does support that, false otherwise. So let's actually implement that on, say, our function sigs contract. Right, so here we might have deployed function signatures, and someone wants to check if our contract, once it's deployed, we hand them the address, and they want to check if our function, if the echo function is available in our contract. Right, so they're querying this contract. They have no idea what the code was that compiled it. All they want to know is, can I echo on this? So what they might do is, because our contract supports the ERC165 interface, which we'll do just like this. Right. So implements like this. Sorry, oh, you can tell that I am not firing all cylinders tonight. It is something's going wrong. Oh, because we're missing the implementation. Sorry, apologies for that. So we've said that it supports ERC165 interface. Because we're inheriting that interface, we have to implement all the functions in it. That means that we have to implement this supports interface function. That's really easy. So I'll copy this in here, and we'll actually implement the body. And right now we can just put return false. Right, it's easy. We'll make sure that we know that we're overriding it. So now all I need to do is work out what this interface ID should be. And the interface ID represents the kind of interface of the contract that we are using. So in this case, the interface of this contract is really one function called echo. So the interface ID in a one function case is really easy. We just return the function selector for echo, right? And that might be something like 0x55. Whoops. So echo might be this function selector, like this. So if someone passes in an interface ID, we want to return true when the interface ID is this and false otherwise. So we can do interface ID equals that, right? And that'll say I can't compare them, but that's fine because we're not going to do that anyway. Right, so that's really straightforward for a single function interface. But imagine if we're dealing with something like ERC20, where we start to have 6 different functions in the interface or 100 different functions in the interface. So we might add a new function here that's called, we'll go echo string. And instead of taking a number, it has a string. Like this. Right? So now our interface has to include both echo and echo string. So what we do now is we take the function signature of each of these, so maybe it's like this, And we do what's called an exclusive or an XOR on it. And that gives us our final interface. So it might look like final interface equals 0x55bb, which is the echo signature, XOR 0xFF77. And I'm not sure if everyone knows what exclusive OR is. It's quite simple. You take two binary strings like this. That look like 0, 1, 0, 0. And then in the output, you're going to have a 1 if the two numbers are different and a 0 otherwise. So here 1 and 0 are different, so it's a 1. Here 1 and 0 are different, so it's a 1. Here they're the same, so it's a 0. Here they're the same, so it's a 0. So we get this. So then we can kind of...
I had a question on line number 14. Function signature is ERC165. Is it inheriting something from this ERC165?
Yeah, so good question. Is used for a few different circumstances. So we might talk more about this another time as well, but it can either kind of inherit actual functions from another contract. So if we had another contract that was like function signatures base, right? And in here we had, say, function echo. If we did is function signatures base, then our contract function signatures now also has that function. So it's inherited it from the parent. When we use is with an interface, so ERC165 is an interface, this doesn't have an implementation. All we're telling the Solidity compiler is that we have to implement that function as part of this contract.
All right, okay.
This contract won't compile unless it has a supports interface function.
Okay, thanks. Got it.
So yeah, you can calculate this final interface by hand if you wanted to. You'd convert this to binary, go through and do all the bits, and you'd end up with the final interface, which would again be 4 bytes, and you could pass it through here. But there is an easier way because everybody got sick of doing this. So the developers built it into Solidity. And you can actually look up the selector of one of these functions directly within the contract. So if we want to find the selector of echo, and we're a developer, we're interested in it, what we might do is we'll create an event that's called signature, and we'll have it emit the function name and the signature of the function, or the selector of the function. I might call it selector. And then in the echo function, I'm going to emit, echo is the name of the function. And then to get the selector, so to get this string here, I can go this dot echo, which is the function, dot selector, like this. And that's going to emit. There we go. That's view. Okay, so initially our echo function was a view function because it didn't change any state. Now that we're using a log, we're actually going to be writing to the blockchain, so it's no longer a view function. That's what the warning is about there. Okay, now finally, if I deploy this contract and run it, we should see a log appear with the actual selector for the echo function in the log. So if I go to my deploy and run transactions, I'll deploy the function signatures contract, deploy it, that's worked. Got this function signatures here, and I'm going to call echo with any number there that I want. So that's worked. And if I look down in the logs here, you can see it's kind of hard to pass. I might copy this to the board. We can see that we've got a single log coming out. The event is signature. We see the echo function name. And then we've got the selector of our function, which is this here. So if we compare that, yeah, our actual selector is that. And apologies, that is only 2 bytes. That's not 4 bytes. So that's what it should look like. 4 bytes makes 8 hex characters. Okay, so that's like the actual echo selector. We haven't had to do the hash manually. And because we can do this like this.echo.selector to get the selector of this function and echo string, to be able to implement this supports interface, we can now do it really easily. And they go through that in the standard. That all you need to really do is something like this, right? To get the actual selector interface, you just do the XOR of all the functions that are available. So for us, we might say that our equals this.echo.selector XOR'd with this.echo string.selector. And then we're going to return if interface ID equals selector. Right, and now we've built out that full supports interface method. And just for fun, we will omit what that selector is. Let's call this one final interface. Looks like selector. Not solidity. Let's go to that. So if I now deploy function signatures again with this new version. Oh, cool. Just ignore these errors for now, for a sec. What have we got wrong? Okay. So we've deployed a new function signatures. If we now call this supports interface, and we'll just put in all zeros for now, with the 0x in front, just to test it. And we look in the logs, we can see that it's calculated a final selector here, which is like this. And then this is our whole function, our whole contracts interface. So we know that this signature here is the kind of signature of the selector for the function signatures contract as a whole. Now we'll remove all this debugging code. This is where it becomes more interesting. This. Okay, I'll just delete it and I'll redeploy now with this actual version. Function signatures. Okay, now I can use this supports interface method on any contract that follows the ERC165 standard to see whether it has the functions that I'm interested in. So for an echo contract, like our function signatures contract, I know that this interface signature or selector should be supported by the contract. So I can paste that in, I can call it, and I get back true. And while this is kind of a really simple use case, we can start to apply this to things like tokens, and that's where it becomes really interesting. So there is, just like there is for the echo contract, there is a selector for the Erc20 interface, and there's one for the Erc721 interface, and so on. But then, because a contract can have multiple interfaces, so it might be both an Erc20 token and also a auction contract, right? Then you've kind of got multiple interfaces there, and a contract that wants to use that other contract can ask which parts of the interface it actually supports. So does it support this part of the token standard or this part of the token standard? And then the contract that's calling can use that information to determine what to do, you know, whether to make a certain call or use a different method instead. So that's quite an abstract kind of notion, but hopefully that kind of makes sense. Is like ERC165 is just a way to give contracts the ability to describe what interfaces they implement. And an interface is a collection of related methods or functions. We actually have a really handy website called the Ethereum Signature Database. It's also at 4byte.directory. And what we've got here is a database of about 180,000 signatures. So those 4-byte codes that look up a function or look up an interface and so on. And so you can use these to kind of look up by the interface ID what the function will be called. So you can click onto like function signatures here, and we can see that, you know, if you're using a function that's called get unique workers index at address, and the byte signature is then that, right? So this is the function selector for this. So if we had a, you know, if we wanted to check if anyone else has published an echo contract, we can actually copy this selector and look it up in the signature database. I don't know if it'll be here or not. No, so nobody's done this. Maybe I will submit it. Pass function signature. Oh, it's annoying. What if I do this? There we go. So we've now submitted a new signature to the database. So if someone else were curious, like what does this signature here mean? They could actually search it and find our echo function. Right, so it's kind of like a community wiki that people can add function signatures to. And this is really useful when you're looking at a random contract on the Ethereum chain. You don't know the code that was compiled to create it, but you want an idea of its functionality. You can look up the signatures or the selectors of all the functions that have been called on it and kind of piece together its functionality. So something like transfer from, for example, which is on almost all Erc20 tokens, will be quite common. You'll find that signature a lot. And by the presence of that signature, you can kind of look it up and realize that this is an Erc20 contract. So are there any questions about Erc165 before I go on? Okay, it's quite an abstract concept, so we'll probably do some more examples of it as we go on. But that kind of wraps up the contracts calling other contracts from last week. So what I'll get into now is how to use Remix more effectively when you're building an application. So the first thing I want to show is the tab that we haven't looked at yet, which is this little graph tab. And this is the static analysis function. So the idea of static analysis is that we can provide it a program in source code, like a Solidity contract, and it will try and detect common errors without actually having to run the program. So maybe, you know, some smart programmer has worked out a bunch of errors people make with Solidity, whether that's not following that conditions affects interactions pattern, right, that we talked a lot about last week. If you don't follow that pattern, you're vulnerable to reentrancy attacks. And that's a mistake that heaps of people make. So there might be a way to kind of programmatically check that so that you can test it before even deploying the contract. And this tool lets us do that. So what I want to do is go back to our simple auction contract. This is the auction we looked at right at the start. It's just a bunch of people bidding on an item, right? And the highest bid wins. So once I've compiled this contract, the simple auction contract, I can go into my static analysis tab, and I start to get all of these warnings pop up. And we can kind of, now we'll go through these warnings and see what they mean. But if you look up in this top part here, these are all the different warnings available, right? So these are all the different things that the static analysis tool can check, and you can toggle them on or off. And then once you run it, or once it auto runs, you've kind of got a list of all the possible errors with your contract. Now, these aren't always necessarily real errors. There's sometimes false positives and things like that. But we can see straight away that if we look at something like the withdraw contract here, it's saying that we are violating or potentially violating the check affects interaction pattern. So that's the same as our conditions affects interactions. I'm looking at it, and so it kind of flags anything that might look like a violation of the pattern. In this case, we're doing the conditions first, we're doing the effects, and then we're doing the interactions. I think it's getting confused about this kind of rollback line. It's thinking that that's another effect, but it really isn't. So it's giving us a false positive. but it's kind of forced us to at least consider that this function might be violating that pattern and then fix it if it is. So if we were looking at our smart contract that had a bid function or a withdrawal function that did violate that pattern, then this warning would kind of prompt us to fix it before we deployed it and before someone hacked our contract. So that's really useful. Other kind of security related flags that it can show, we've got a warning about using block.timestamp. And this is a very common warning because there's a slight issue with using the block.timestamp variable. When you're using this variable in a smart contract, you're asking for whatever the current time is in the block that the transaction has been executed in. So remember, a block is executed every, say, 2 seconds. It wraps up a bunch of transactions, and it has a certain time associated with it. Because of the way Ethereum is designed, a miner, so someone who's creating new blocks and including transactions in it, can subtly influence this timestamp. Right? So they can make it earlier or later if they want to. And they can then use that kind of ability to alter the timestamp while they include your transaction to attack your contract if you're not careful. So let's say I was a miner and I was really interested in buying a certain house, and there was an auction going on the chain for the house. What I could theoretically do is, if we got close enough to the end of the auction, I could place a bid, which would be the highest bid, and then I could subtly alter the timestamp so that the auction ends earlier than it otherwise would have. So I would make block.timestamp larger because I happen to mine that block, and I could win the auction without letting someone outbid me. So using block.timestamp is always something to be a bit careful about because it can be influenced. What you can do instead, if you're worried about that, is just use block.number. Right, so block.number achieves pretty much the same thing as block.timestamp. So you just kind of have to convert between them. You know, if you're asking for, 10 minutes, that might be, 50 blocks, right? You just do that conversion. But the miner can't change block.number because the block numbers are in order always. So it can be a bit more secure that way. It prevents someone attacking it. So what else have we got? We've got more block.timestamp things. We've got a warning for using low-level calls like send. So send is a lower level call, and if we were to read this, it would explain that you might want to use the transfer function instead. In this case, send is appropriate, but transfer is also possible. And the difference between them is quite simple. If I have a payable address, so an address that I can send Ether to, and I use send with an amount, then that's going to return true or false, whether it's successful or not. So it's essentially a Boolean, right? Now this will be true if it was sent, if it was false. So if the contract rejected me sending the money, then this would just become false and it would continue on. If instead I use transfer, like this, it no longer returns true or false. Either it succeeds or the whole transaction fails and rolls back. And that's what this warning is telling me, that if we were just going to do in here a reverse anyway, right, or a require false, right, if we're just going to do that anyway, then we just use transfer because we didn't need to do the check. So it's giving us that nice little warning there. Then outside of the security section, we then get on to kind of the gas section. And here it might warn you if you've got certain functions that will use a lot of gas or that will be inefficient. And it will tell you to avoid loops in your functions as well, which we've talked about previously. Then we've got the miscellaneous section. So if I click on this one, I will just ignore those for a second. So here it's just giving us a warning, right? Requirements, so using this require statement, is useful if we want to return an error message to the user. So if this is kind of a functionality of our contract that it should sometimes be impossible to place bids because the auction has ended, which is true in our case, then you should use require so you can return a nice error message. If you wanted to do kind of a sanity check or making sure that something was always true in your contract, and if it was ever not true, you should always fail. It's not expected at all. It's not like a user interaction thing. Then you can use assert, and in here you can have, if it was false, it would roll back your transaction. However, in practice, pretty much always use require because you get a nice error message. It's going to warn us that many times. And that's all the warnings we've got for this contract, which is awesome. If we look at the available security things, we've got, watch out for using self-destruct, watch out for using a block hash, which can be influenced by the miners the same as the timestamp can, and some other things. And, it's even got checks for using Erc20 contracts. So it's quite useful just to get kind of a general overview of things that you should check in your contract. Often, as you've seen, they're kind of false positives and you don't really need to worry about them, but it is nice to just run that through and check. It will find some common mistakes. Beyond kind of the Remix static analysis tool, the Ethereum community is working on a bunch of other different static analysis tools. Because smart contract codes are so bug prone and it's so dangerous when they do have bugs because it often costs a lot of money. Static analysis is a really kind of important tool for testing contracts. So there are platforms like MythX, right, which will analyze your contract and perform a lot more kind of sophisticated analysis than the Remix one, and it will give you kind of more useful errors as well. Right, so it'll output things like the contract can be killed by someone against your will and things like that. Right, so that's all quite interesting. And you get these nice reports as well. Okay. Any questions on the static analysis tool? All right, what we're going to do next is we're going to look at the debugger. So the debugger is something that you'll use a lot when you're trying to work out why your contract isn't working. It's this little tab here, and it's kind of complicated to look at, so we'll go through it. So to do that, we'll get another contract. I think I might have it already, and it's called donate. So this is a very simple contract. We don't need to go through it line by line. Essentially, anyone can donate to this contract, maybe as a charity, right? So people all around the world can donate Ether to this contract using the donate function. And then the owner of the contract, so the address of the charity who runs this contract, can then pay out money from it using the move fund function. So they might want to pay staff, or they might want to fund an aid mission to a third world country or something like that. So this is kind of like a smart contract based charity. And we'll use this as an example of how to run the debugger and find potential issues with our transactions. So what I'm going to do is I'm switching back to my deploy and run transactions. I've compiled donation and I'm going to deploy donation. Right. And I'll remove the rest of the contract so we don't get confused. We now have this deployed donation contract, and whoever created this contract is set to be the owner. So now let's donate some money to it. I might personally donate 1 Ether, let's say. I've donated that successfully. Someone else might want to donate 4 Ether. They're feeling really generous. So I'll do that donation. And then we can call get balance and we can see that we've got 5 Ether stored in this contract. Then the charity, who is this first address here, wants to actually pay out a staff member. So they'll call this move fund contract. Now we've got this only owner modifier here. And what this does is it checks if whoever is sending it is the owner. And if not, it doesn't run this function. So we'll just skip over it. right? And you can see that here in this modifier. Might be a bit more helpful to see it written like this. This is exactly the same. Before we kind of run the move fund function, we have this if statement that wraps it around. If the sender of the transaction is the same as the owner of the contract, then insert all of this code. Otherwise, just do nothing. Right. So let's say we are someone who's not the owner. You know, the charity is accidentally using the wrong account, and they're ready to pay out a staff member. They've got their Ethereum address, and they're going to use the move fund contract, the move fund function. So they paste in their address, they paste in an amount, they click transact, and it's passed, right? So the transaction worked. Then they click get balance, and they notice that no money has actually been paid out, right? So that this is, as the charity, extremely confusing, right? The balance hasn't decremented, so it's still 5 Ether, but I have called move fund, right? I can keep calling that. So the reason that this is happening, as we all know, is because they are not the owner of the contract, so it doesn't run anything at all. But if you kind of weren't sure what was going on, this is where you would break out the debugger. You know, once you've got things you're not quite sure of, we'll open up the debugger, just like you've got in, you know, JetBrains or Eclipse or whatever you use for Java, right? And we've got this handy little debug button, which will open the debugger for a specific transaction. We can also manually switch to the debugger tab, which is this little bug here, and paste in the transaction hash of any transaction that we want to debug. If I look at, this is the transaction we just made and I've clicked it, I've got this transaction hash. So I can also copy this in, paste it here, start debugging, right? So once we're debugging, we kind of get presented with a whole load of information. The first thing that we've got here, if we're just looking at the kind of information, all of this is the current state of our contract and of the contract's memory and storage. You know, so at this point in time in the transaction, where we're looking at all of this information, we have a function stack first, and this tells us what function in the contract we are in. So we've called move fund, and so we're currently executing the move fund function. If move fund, for example, called add giver, right? So we've got a call in here that said, oh no, I've broken the debugger. You can't edit it while you're debugging, unfortunately. So if move fund then called add giver, then we would add another function to this stack, and we would see that we're in add giver and we've come from move fund. So this helps you kind of orient the order that functions are called within your contract. We then have this Solidity locals. This is any value that is local to your function. So if we look in the move fund contract, balance here is a local variable, and this balance here would appear in the Solidity locals section. Then we have our Solidity state. This is all of the state that's in storage for our contract. Remember that we declare things in storage outside of any function, so they're all up here. We can see that we've got an owner, which is an address. We've got an array of people who have given to the contract and then how much they've given. And we can look at this Solidity state and see that when this transaction started, these were the actual values stored in these storage variables. So this was the owner, 5B, 38, whatever. These were the givers so far, and they donated 1 ETH and 4 ETH respectively. And you can see how this changes over time as well. So that can be quite useful for working out bugs as well. Then we get to this little window here, and this is probably the most important window in the debugger, so it's annoying that it's so tiny, but this is the actual EVM instruction that is being executed right now that has, you know, because this is the Solidity code, it gets compiled down to a list of EVM instructions, which are here. So although it's highlighting this line, which is kind of where we're running at, what's really happening behind the scenes is we're running the push one function, or the push one operation, opcode. So you can see exactly what that is. We'll talk more about these ones in a second. We've got step details. So you can see, for example, how much gas is remaining in this transaction before you hit the limit. We've got the stack. We've got memory and we've got storage. These are all different places for storing values and data. We've talked about memory and storage. We haven't really talked about the stack. So I'll talk about that in a second as well. We can see what's in memory. This will be things like the balance, right? It's local to a function. It will be discarded at the end of the transaction. But things in storage are the ones that are kind of saved on the blockchain. And that's our owner, givers, and values. So that's the actual storage data there as well. Call stack is the same as the function stack, just not decoded into nice names. And then we don't really need to worry about the next of these ones. Okay, so to actually control the debugger, we kind of use this little interface here. So you've got a timeline of the transaction here, and this shows you where you are in the transaction. And if we think of a transaction as like a list of these EVM instructions, so we'll push one, we'll dupe one, we'll S-load, and so on. We can kind of scroll through those instructions using this little toolbar here. That's quite nifty.
Well, I just want to know, can we set a breakpoint here and debug step by step?
Yep. So if you click on any of the lines like this, right, you can set breakpoints. Just click on the margin, and then you can use this run into a breakpoint button. Now, in this transaction, it's failing before that breakpoint, but maybe I can try it like this. So I'll go right back to the start of the transaction. I've set a breakpoint on this if statement here, and I'll run it until the breakpoint, and it's stopped me there. So yeah, that's really easy. You've essentially got the breakpoint option, and you can jump between the breakpoints. You can use these little arrows to step forwards and back by one instruction. So we're at push one here, instruction 160. If I use this, we'll go to 162 and we're at dupe one, right? So we're just going back and forwards. And you've got this one, which is step over, and this will kind of skip a function call. It's a little bit weird behind the scenes, but for example, I just wanted to jump straight over this line rather than going into how an event is actually emitted. I could use step over. So you can kind of use this to step through the contract. Now.
So in the example you showed 160 is the push. So when it executes the modifier function, then it shows the behind the scenes functionality. Yep. What does it mean? 160 push 100?
Okay, yeah, let's talk about that now. So this is the actual instructions that are executed by the Ethereum virtual machine. So on the left here, we have the instruction number, right? So in our program, we have something called a program counter. And if you've done any kind of assembly language programming, you'll be familiar with this. We can really think of our program as something like this. We might have, say, dupe one, push, and then we have a number like 0110. Right? And if we think of each of these instructions are something like 4 bytes, I don't know how many bytes it is. I should know that. 2 bytes or 1 byte. 1 byte. So each of these instructions is 1 byte. Then we're going to have any number of arguments to the instructions. And in Ethereum, you either have an instruction with no arguments up to an instruction with 3 arguments. So you might have like a push 3 function. And then if we have kind of 3 arguments like this should be like 1. Right, then this all gets added into code and then gets kind of stuck together. So it might look like this. Now we want to run through this code here. So we want to first execute dupe 1, Then we want to execute push one or push with this argument and so on. So we have something called a program counter, which gives us the address of the instruction in our list. So we start off with a program counter of 0 for dupe 1, which I'll now split out again. Then push is at 1, so it's at 1 more byte. Then the next push, we've gone 1 byte, 2 bytes. So we're now at 3. Right, so this program counter kind of tells us where we are in the program execution. So if I restart the debugger, we can see that this push 1 instruction here is using the instruction push 1. It's been passed in a 0 as its only argument, and it is at position 160 in the program.
Okay.
Now, when we actually want to start understanding what push 1 actually does, right? A really helpful resource for that is this ethervm.io. And this is where we can actually look up what each of these instructions does. So I can look up, say, push 1, and it goes on my list here. So that's quite small. But for each of the instructions, this is what it kind of includes in this table. We have the name of the instruction, push 1. Then we have the actual byte that represents that instruction. So push 1 is 60, which means that when we're writing our code, if we had push 1 and we're pushing a 0, that would become in machine code 6000, right? 60 is push 1. Then we have all the different arguments that it takes. So here it takes in a single argument, which is a 8-bit integer. And so push 1 takes in up to 8 bits long as a number. Then we have a description of what it actually does. So here it takes that argument and it pushes it onto the top of the stack, which is that third memory location that we're talking about. And that actually might be a good opportunity to talk about those memory locations. So if I just go to Paint. So we've talked about kind of 2 types of memory already. We've got storage. And storage is the data that stays on the blockchain after your transaction is run. So it's persistent across transactions. Now, this, you can access it at, there's a bunch of addresses in storage. It's addressed by, like the location is a hex string. So maybe at this location here, you'll have data that looks like hello world, right?
Okay.
So that's pretty straightforward. Right, and this stays across transactions. Then you have very similar memory, which works exactly the same as storage. So it's addressed by a pointer to the memory location, but it doesn't last after a transaction. It's kind of thrown out. Now, the third thing, which is what all the instructions, the opcodes mostly operate on, is called the stack. It's the same as if you're using C, you're probably familiar with the stack or assembly. And the stack is a way for opcodes and operations to share data that's only going to be used in a really kind of local setting. It's not going to last for the whole transaction. It's definitely not going to last on the blockchain. And the stack starts off empty. And then you can kind of add in values to it. So you might first push onto the stack 256, right? So now the stack has 1. Let's do a better diagram. Sorry. So we'll say this is our stack, and it starts off empty. And when we add data to the stack, we add it to the top. When we remove data, we remove it from the top. So it's either growing up or shrinking down. So you can't really read like things at the bottom of the stack when there's things on top. It's like first in, last out is the idea. So our stack might look like initially empty. Then we might add a number to the stack like 56. Then we might add another number, which we could say 89. Then we might want to add these two numbers together. So what will usually happen is all of these opcodes that will kind of go through that are actually the Ethereum virtual machine instructions, they usually operate on arguments in the stack. So if I have, say, the add instruction or the add opcode that adds two numbers together, it might take the top two values from the stack, add them together, and then put that result onto the stack. So our result then would become 56 plus 89, whatever that is. And the add instruction has done that. So when we're looking at the push one instruction, which was the example I'm looking at, all that's really doing is adding one number onto this stack. So we've got kind of push one, and then we add. Now, if we look at our description, that's exactly what it does. Pushes a 1 byte value onto the stack, or push one. Let's look up something like add. Right? Here's add, and it's saying that add takes in the top two values on the stack. This is our stack input, A and B, and then it ends up being A plus B on the stack. Right? So that's exactly what we showed there. So at a really, really low level, all your code does is kind of compile down to this list of stack instructions, and also a few instructions that save from and load from, save to and load from memory and storage. Does that make sense?
Yeah, makes sense.
Okay, cool. So if you're ever confused, you can actually just look up in that table. I'll send this link and see exactly what each of those individual instructions are doing.
Okay.
All right.
Also in here, like a modifier only owner in this method, if I just return true, does it make sense? Or
if you return true from only owner?
Like if message sender equals to owner, if that match, then I send true.
Yeah, a modifier doesn't return a value. What it does is it kind of gives you a scaffold to insert code from the function that modifies. Okay. So only owner here has been applied to modify the move fund function. So
basically, when I call the move found function, then it will check first whether I'm owner or not, right?
Yes, exactly. Yeah, it will run all the modifiers which have changed this code. So it'll first run the modifier check. If you're not the owner, then it's just going to continue onwards.
Okay. So if that match, then rest of the code will execute. I mean, unit balance, and if amount less than balance, like number 32 line, this code will execute if I am the owner.
That's
Otherwise,
right.
it will not execute.
Yeah, exactly. And we can test that. So if we go to the owner of the contract and we run this move fund again, which has succeeded, I'll go into the debugger. I'll put a breakpoint on the balance line here. I'll run to the breakpoint, and we have now hit that breakpoint. Right, so we're now here. We can start to kind of step through the move fund function. As we go, it's very slow, but we're in move fund. And the reason for that is because message.sender was the owner. That all passes. We hit this underscore, and that underscore says insert all the code from move fund.
Okay.
So let's do another example of debugging a failing transaction. We've got this kind of checks in here. So you can only move an amount, or you can only pay out an amount using this move fund function that's less than or equal to the amount of money stored in the contract, right, which makes sense. If that fails, then we're going to revert the transaction. So if I am the contract owner and I'm trying to transfer heaps of money, yeah, we fail. And we can kind of work out where that's happening. Like say we'll set a breakpoint here, we'll jump to it, and then we will start to, oh, we've jumped all the way. The Solidity Debugger can be kind of annoying with breakpoints sometimes. Sometimes you just have to go through the instructions manually if it's annoying.
Yes.
So right now we've hit revert on line 389, we've hit the revert opcode, which is here. And so you can kind of use it to debug where exactly things are going wrong.
Okay.
You'll also see if say you wrote a function that used all the gas available, like hit the gas limit and it reverted because of that, you would see that in this remaining gas section, you would see it hit 0. So you can kind of work that out. But the debugger in general is a good way of working out exactly what is going on at a lower level. You know, when you start to worry about things like gas optimization, where you want to make your contract as cheap as possible to run, you will have to start worrying about what instructions are generated by the contract compiler. You know, you might use an instruction called sload, which is more expensive than storing in memory or something like that, right? And you can kind of debug it like this and get a pretty good view. But mostly it's useful for looking at the locals, so the local variables and the storage variables of your contract. So, what should I show next? Are there any more questions about the basic use of the debugger before I continue? Okay, cool. So what I want to do now is use this debugger to show in a little bit more detail how Solidity events work. So if you remember, an event lets us kind of log to the blockchain and notify everybody who's listening on what's occurred. So in the auction, we had an event when we had a new highest bidder, and we had an event when the auction ended. And so what I'm going to do is a super simple contract, which I'll just call events.sol, and it will look like this. So the first event here is called unindexed, and this is like the ones we've seen before. So this event takes in 2 arguments, a sender and a message. The sender is the address of whoever sent the message, and then the message is hello world. So if I call this emit unindexed function, I should see in my logs 1 log, which is the unindexed event with this data. Right, and I can compile, deploy, look at the logs from this transaction. Oh, I haven't called it, sorry. Other events. I'll call emit unindexed. And I can see that that's kind of emitted here, right? So I've got event is unindexed. Sender is the address that I'm sending it from. And then message is hello world. But what we can do is use the debugger to kind of see exactly how this event is being emitted on the blockchain. So I'm going to debug this transaction, which is lovely. And I'm going to start stepping through it. So clicking on these instructions, and I can kind of watch as we hit each of these things. So for example, there's an add, right? And if we're looking at our stack here, right, which is the same as the stack diagram I showed, it's just upside down. So it starts from here and is down to here now. We're about to run the add instruction, for example. So we should see 7 and 8, these 2 values get added together and end up the added value beyond the stack. So try that. There we go. So that's now the addition of those two values. All right, we'll continue on doing this and so on. And what it's doing here is it's doing kind of a bunch of manipulation to set up the message.sender and hello world in memory. I'll just keep going until I find the instruction that I'm looking for, which is, I can probably scroll. Go backwards. Here it is. Log 1. So the log 1 instruction is what's actually causing this event to be emitted. And if we go to our instruction list here, we're going to look up log 1. And we can see that it takes in 3 arguments from the stack. Offset and length kind of, there's 2 parts to a log. So if we have a log, which I'll just make on a new page, which we can call interchangeably a log or an event, we have firstly a topic. And then we have data. Now a topic is a really short, I think it's, how many bytes? 4 bytes or 8 bytes maybe? Not sure. But it's like a really short string that kind of describes what that log is about. Then all the data that's associated with the event or with the log is added in as this kind of data object. So when we're emitting this unindexed event, the topic of the log is that it's unindexed, right? It's the name of the event. Then the data that we're kind of adding onto the log that we want to share with everyone, that we want to notify them of, is the sender and the address. And so we can see we've used that log1 instruction, which takes in the topic from the stack. So we can see that it takes in 3 arguments from the stack. The third from the top is the topic. And we can actually look that up on our stack here. We can see this is the topic. Right, so it's that. It's a lot more than 8 bytes. I don't know how many that is. 32? Doesn't matter. Right, this is the topic of our transaction. And the topic here you'll see is a hash, and it's calculated just the same as a function selector. So it's the hash of unindexed address string. The hash of that equals the transaction, the log number, sorry. Jump back to where I was. Then it also takes, if we look back at log 1, 2 more arguments, and this takes off an offset and a length, and this describes where in memory to find the data for the event. The data we remember is an address and a string, and they are located collectively at kind of this memory position on the stack. But we don't really need to remember all that. All we need to remember is that the log creates a topic and then it adds any amount of data onto it, right, from memory, which is great for us users because we can start to listen for these logs as they come off the blockchain. So if we're interested in any unindexed event or any transfer event, we can kind of listen for that. But you might then wonder, what is the difference between a topic and data? Why does the topic have to be something special? And the reason that we kind of separate the topic and the data is because if the topic is much smaller, then Ethereum can make it really easy to search by topic. So since we know that a topic will always be kind of a really short 32-byte hex value, for example, we can build in, and developers have built into Ethereum, the ability to search by topic. Whereas with data, which can be much bigger, Ethereum has no inbuilt way to search by the data events, but you can search by the topic. So that's, so the topic is searchable. What that means is you can look up, you can take an Erc20 token contract, and you can search your Ethereum node for all of the events with the transfer topic or with the approval topic. you can't really search all of the events that were transferred from a certain person because that's in your data and you can't search by this. Okay. Now, obviously, this is quite a restriction because it means you can't do kind of searches of anything complex, right? You can't search by, as I said, I want to see all transfers from this address to this address and like search and filter on those events. So what the Ethereum developers did was they kind of extended this structure and they've actually allowed for up to 4 topics per event. So we can extend this out. Our events all have data, right? And that can be either 0 bytes or as many as you want. But you can also have up to 3 optional topics. So maybe these look like that, right? And these are optional. And you can also search by these topics. So what you could do is you could put into the first topic the name of the event, transfer. And then in these 3 topics, you could put information that you want to be searchable by. So the address of the person who is sending the token might go into the first topic. The address of the person who's receiving the token might go into the second topic. And then the third topic could be the amount, right? And then people can search for, say, all events that transferred 50 coins, or all events that transferred 60 coins to a certain address, things like that. Then you can have extra information about that event in the data that the user will then be able to read that they didn't need to be able to search by. So by adding more topics, we can really efficiently search for certain events. Now, to add those topics, Solidity makes it really easy. All we have to do is add a specific keyword, which is indexed, to the event data that we want to put into a topic. So by default, the name of the event goes into the first topic. Then we start filling the topics with anything that's marked as indexed. It's called indexed because Ethereum builds a search index, which makes it efficient to search on it. So if we're looking at our unindexed event here, it's got a single topic and then everything else is in data. If we look at this index function, it has a topic containing the name indexed or the hash of the name. Then it has a topic containing the sender address. Then it has a topic containing the message. So you can search by name, by sender, or by the message. And we can actually see that if we call now emit index, which is going to emit this one. So I've called emit indexed. I'll look down and I can see I've got the same log information mostly. I'll talk about the mostly in a second. I can see this is the address here that has been emitted. And if I debug the transaction and I jump to the end, we are now using the log3 instruction, right, rather than log1. If we look at log3, we can see the only difference is it supports up to 3 topics on the stack. Right, so Solidity has worked out that we've got 2 indexed arguments. We've got the name of the event that makes 3 topics. So, we can use the debugger to explore behavior like this. Now, your topics are how long? Something like this, which is, I should know this off the top of my head, but 64 characters long, which is 32 bytes. Right, so if a topic can be up to 32 bytes. For something like an address, which is 20 bytes, that gets inserted directly into the topic. So if we look at our arguments to the function here, we've got the event name, which is indexed, then we've got 2 args. The first one is the address of the sender. 0x5v3, that matches the address that we used to send it here, which is message.sender. So that's worked perfectly. But hello world, or really any string or any bytes value, which is called something called a reference value. So it kind of points to memory or storage. It doesn't store hello world in memory because it could be any length. It could be 5,000 characters long. Any reference value like that, if you use the index argument, has to be squashed to fit into that topic, which is 32 bytes long. So instead of including hello world, the string, we instead include the hash of it. And we can see that here, argument 1 is the hash of hello world. And we can probably verify that. We'll take hello world. We'll open up our hash function, paste it in. We can see it starts with ECD, and that is the value that has been logged. So you might think that it's best to always put things in the indexed, so that it's in topics and so it's searchable, but it is a trade-off because you can't recover the message then from the log. You can only search by the message. You wouldn't be able to take this hash and go, oh, the original message was hello world. If you wanted to search by the message and also include it fully in the log, you could add it again, right? You could go message again and have the second time you use it be unindexed. So the first one is hashed and searchable, it's in a topic. Then the second is in the data section of the event. So you'll be able to see it, but you won't be able to search by it. And you can kind of build the best of both worlds there. If we look at the Erc20 interface, you will see if we look at the events here, the official Erc20 events have indexed values for the from and to address when you're transferring. So you can search by the sender and the receiver. And for the approval, the to addresses are also indexed. Right, so if we're faithfully fulfilling the Erc20 contract interface, we have to add those indexed arguments. It's the same for a lot of interfaces. Are there any questions on the events? Okay, awesome. So we've got maybe half an hour left. So I might take this time now, so we're not pressed for time, to talk about, I guess, the first assignment smart contract. And the idea of this assignment will be, I will provide the interface for the smart contract. So, all the functions available will be there. And then your job is to implement those functions. So just to fill out the code for it. The way it will work is I'll kind of go through and describe it. Then you'll take this home. It's due by the next session, so next Wednesday. And we'll run the assignments on GitHub. So I'm sure that all of you have a GitHub account, but what I would like you to all do probably straight after this or tomorrow or something like that, create a repository that you can just call Women in Digital Blockchain course code or something like that. And then when you finish writing the contract, add it to your repository and push it, and then share these repository links with me so that I can kind of go through the submissions. Have you all met Heather Swope? I'm not sure. I know Akia you have. But she is another trainer. She's in Amsterdam, and she has agreed to help me with reviewing your code and providing feedback, finding bugs and things like that. So by putting it in GitHub, I can share it with her as well. And then we'll kind of provide feedback on the actual GitHub submission. And also, if there's any kind of common mistakes and things like that, we'll go through that in one of the sessions. So with that being said, here is the first contract. Now, we've been looking at auctions a lot. So, one sec, sorry. We've looked at a standard auction, but what I wanted to do to keep the auction theme going is implement something called a Dutch auction. And a Dutch auction is essentially the reverse of a normal auction. In a normal auction, your bids kind of go higher. In a Dutch auction, you start off at a really high price. Anyone can bid at any time. If they bid whatever the asking price is, they win, the auction's over. Right? So if we start a Dutch auction, I say 10 million is the starting price. Someone bids 10 million, they've got it. If nobody bids, however, after a certain time period, so an hour maybe, then the price lowers by a set amount. Now it's at 9 million. Anyone can bid. If they bid, they win. Otherwise, after an hour, it gets lowered again to 8 million. And so on. It keeps lowering until either someone bids and wins the auction, or it hits a minimum price or a reserve price. And after that reserve price is hit, then the auction ends without anyone buying it. So the auction is kind of abandoned. So if we look, if you want a full description of what a Dutch auction is, we have it in Wikipedia. And it says, it's an auction where the auctioneer begins with a high asking price, lowers it until someone accepts the price, or it reaches the reserve price and fails. So hopefully that makes sense. And there's a little description in here, but we'll be implementing a contract with 2 different functions and plus a constructor and 3 events. So this Dutch auction contract should be created by someone who wants to sell something. It could be a house event. So some of the parameters that they need to set in this contract are listed here, and you'll fill in this constructor with the parameters that it takes in. You can input that. It should take in the price that the auction starts at. So this is the highest price. It should take in the amount to lower each time we lower it. So this might be 10 million as the starting price. We lower by 1 million every time we lower. It should take a time interval in seconds that has to pass between lowers. So we might set that to be 60 seconds. Then if there's no bids for a minute, we can lower the price by 1 million. Then after another minute, we can lower it again, and so on. Otherwise, it would just get lowered too quickly. And it should also take in the lowest price that the buyer or the seller is willing to sell their item for, so the reserve price. If we keep lowering and lowering and we hit that reserve price, we want our contract to self-destruct. We want the auction to be abandoned and not sell the item. Those are kind of the setup parameters there. Are there any questions about that concept so far of a Dutch auction? Cool. All right. So the 2 functions that are available for the users of the contract are obviously in this interface, the Dutch auction interface. The first one is bid. This is really easy. If someone bids, then they have to send an amount of ether. If that ether is equal to the current price of the auction, then they win the auction. Their money should be sent to the beneficiary of the auction. So the person who is selling it, which is the creator of the contract, and the auction ends. So it would emit this auction ended event. So bid is easy. If something goes wrong, so they haven't sent enough money, for example, then we will reject the transaction. We'll use a require and we'll revert the transaction. The other available function is lower, and anyone can call lower, so it doesn't have to be the contract owner. But what lower should do is should check if enough time has passed since the last lowering, so if that time interval has elapsed. And if so, it should lower the current price of the auction by the amount that we're lowering. So 1 million or 50 million or whatever it is, right? And anyone can call that, but it has to wait a certain time between executions. If that eventually lowers until it hits the reserve price, which is set in the constructor, then it should self-destruct the contract after emitting an auction abandonment event. So auction abandonment means there was no winner. The auction failed. Nobody bid. Lower should also emit this asking price changed event every time the price changes. And this means, like you're on eBay, right? You kind of subscribe to this auction. Every time the price lowers, you'll get an alert, which is this asking price change. And you'll be able to see what the new price is, and you can decide whether you want to bid. You can see in here, we've got these indexed arguments. Just noticed one thing. There's one bug in this. That is anything that's indexed in an event has to come before the non-indexed ones. So it should look like this. Just update that quickly. So when we change the asking price, we want to log the person who changed it, so message.sender, and the amount, which is the new asking price. When the auction ends, we're going to log the winner or the address of the winner and how much they paid for it. So, are there any questions about that? Is that okay? So I'll send this straight afterwards. And ideally, everyone will send me their GitHub, the GitHub repository they set up straight away, just so that we're ready to go. And then you can kind of just upload the contract whenever. And also, if you've got any questions at all during the assignment, just post it in Telegram where I can help or Heather can help and so on. And hopefully this is difficult enough to be enjoyable and not too easy or too difficult. So any questions about the assignment? Great, okay. So I will then continue with our remix exploration. Just wanted to get the assignment away so we didn't run out of time for like questions, but I'll send that around afterwards. There's a couple more features of remix that are really useful for us. And one of them that we haven't looked at yet, and it's a feature of the Solidity compiler in general, is the optimizer. So right now, every time we compile our contract, right, with this compiler tab, we've had enable optimization off by default. So if I just pick a different contract, let's go Coin, for example. Right, we've done this without optimizing it. Now, the optimizer in the Solidity compiler is pretty smart. And what it will do is it will try and compile and arrange those Ethereum opcode instructions so that they are as efficient as possible in terms of gas. So without optimization enabled, it kind of emits the most straightforward sequence, like the easiest to follow sequence of instructions. But there might be more efficient ways to do things. For example, one of the things that you could do if you were kind of optimizing by hand is if you had a for loop that looks like, let's make a new tab so I can, say you had a for loop that looked like this, uint256 I equals 0, I is less than 3, plus plus. And for each of these, we're going to emit an event. So we're going to emit an event 3 times. Now, if you just ran this without an optimizer, the compiler would kind of generate the instructions to form a loop and to loop through it and so on. If you ran it with an optimizer and the optimizer was smart enough, it would see that this will always run 3 times and it will convert this to just look like this, which is cheaper from a gas perspective than running the loop, right? Because you know it's always going to run 3 times. But this is obviously a lot more annoying to maintain from a developer perspective. So the optimizer should be able to make these transformations for efficiency without sacrificing how the developer writes their code. And in general, it's actually pretty good. The Solidity optimizer works pretty well. So what I wanted to do with Coin is kind of demonstrate that. The first thing we'll do is we will deploy the Coin contract, which is just the standard Erc20 contract that we've done so far. I will select that here. I'm going to deploy it with, again, 1,000 total coins. Deploy it, the transaction passed. And we can see that it used 837,000 gas to deploy it, right? So this is like its complexity, its size, and how long it took to run the constructor. So this is with no optimization. Now, what we'll do is we'll compile it again, but this time we'll enable the optimizer. So I tick enable optimization, recompile it. The code will function exactly the same. It's just going to generate a different sequence of opcodes to represent that code. And I'm going to deploy the new optimized version of the contract. That's exactly the same. Look at this. And we can see it is now using 400,000 gas to deploy. So it's given us essentially half price by turning the optimizer on. Optimizing also works for function executions. So if we optimize with, we'll turn the optimizer off to start with, compile cable coin again. Deploy with 1000. And we might measure the transfer function. All right, so I'll transfer 500 coins. Like this. And it cost me 52,515 gas. So this is transfer, no opt. 52,000 gas. Let's see what the improvement is with the optimizer on. So I'll turn it on. So our second one here is the optimized version. I'll do the same transfer. And we can see it has reduced that cost down to 36,000. Now, when you're dealing with bigger, more complicated contracts, this is quite significant in terms of cost savings from like a real world money perspective. So you want to optimize as much as possible. You might have noticed that we've got, when we compile it, we've got this number here, which is a parameter to the optimizer. And the number in here is an estimate from the developer perspective of how many times this contract will be run as a whole. Now, the reason for this is because the optimizer and the compiler can make different trade-offs. Maybe you're going to deploy a contract once, and it's a really large contract, but then you're going to use it very, very rarely. So the most expensive part will be deploying. Then what you want to do is you want to optimize to have the smallest code possible so that it's cheapest to deploy, even if that makes some of the functions a bit more expensive. However, if you're only going to deploy once and you're going to use it heaps and heaps and heaps, you're going to call the functions heaps, then you might want to make those functions as cheap as possible and pay a little bit more for the deployment. So this number here lets you tweak that. If you just wanted the initial deployment to be as efficient as possible, you would set that number to 1. You'd say, I only want to run this contract once. If you wanted to focus on a contract that's going to be run thousands of times, you could bump that number up to 2,000, for example. And if I did run this, I did it before, you can see that let me show you. These are my stats from before. Execution is the deployment cost. Transfer is the cost of transfer. So with an estimate of 200 runs compared to an estimate of 1 run, we can see that execution has become cheaper when it's 1 run. So the deployment is cheaper, which is what we'd expect. But the transfer is more expensive, which is again what we would expect. So we can instruct the compiler to make that trade-off for us, which is really cool. Now you might wonder why not just have the optimizer on at all times, because it can make debugging really annoying, because it does weird, tricky things with the opcodes that aren't really intuitive to a human. So generally when you develop, keep the optimizer off, do all your debugging and testing and so on, and then optimize for the actual release, when you release your code to mainnet. I don't think there have ever been real bugs in the optimizer, but it is theoretically possible that the optimizer could break your code if there was a bug in the compiler. So it might also be a good idea to optimize and then check that on a testnet as well, perhaps. Okay, now there's the one more thing that I wanted to go through in Remix is how to build tests. So there's a whole kind of unit testing feature, but I've gone through a bunch of different concepts tonight, so I might not overload that in the last 16 minutes. So maybe we'll take this time to do a quick review of what we've covered today. We've just covered the optimizer, which lets us make our contracts more gas efficient. We've covered the static analysis tool, which gives us warnings on our code that we might want to check, things like the conditions and effects interactions pattern that we might want to check before we deploy our code to find bugs. We've looked at how function calls work under the hood. So when we call, say, the total supply function on a contract, really what we're doing is we're looking up the function selector of total supply. So we are taking the hash of total supply and all of its arguments. We get a function selector from that, and we use that to look up the function in the contract. And then we can take this concept of function selectors and combine them to create an interface selector, or a 4-byte code that represents the interface of a contract, whether that's Erc20 or Erc721 or your own custom interface. We can then use that interface code with a standard called Erc165 to allow our contracts to ask other contracts what sort of functions they support. So I could ask a contract, are you a token? Get back yes or no, and then change what I do based on that. And where did we implement that? I think it was in function sigs. All you need to do to support the Erc165 interface is write a function like this. So supports interface, takes in an ID, returns true if that equals your interface ID, false otherwise. You could also actually have this, you might support multiple interfaces. So function signatures might also be an Erc20 token. And you can really easily signal that by just going like this, right? Either interface ID equals the echo interface, or it equals Erc20 token interface, which we could declare in a variable, right? So supports interface can work for multiple variables too. The other thing you can do is I showed last week the Open Zeppelin library of smart contracts. We go to our Open Zeppelin contracts. If you look at utilities section, in the introspection section of the Open Zeppelin contracts, they have an Erc165 contract, which you can use as part of your contract. So you can make this support Erc165 really easily. Then if you wanted your contract to be able to check other contracts and see what interfaces they support, you could use this Erc165 checker contract, which just checks other functions. And so on. So, a lot of this work is done for you. And then what we spent kind of most of the time talking about was the Solidity Debugger. So it gives you an ability to inspect the actual instructions that were executed as part of a transaction. So moving through those opcodes, we've got a really nice list of opcodes on this website, the virtual machine opcodes, and it tells you what the inputs and outputs are of each opcode and a little description of what it does. And you can trace the execution of your transaction inside the debugger, see the opcodes, and also see the values in each of the different memory locations. So we had the storage, which was persistent across transactions. So it's addressed. Each chunk of data has an address that you look it up by, and it lasts across transactions. We've got memory, which is addressed just like storage, but it's not persistent. So after the transaction is over, it gets wiped. Then we have the stack, which is used by the opcodes to kind of use data really locally. It's kind of constantly in flux. It's not designed to last for a long time. And most of the opcodes either add to the stack, remove from the stack, or operate on the stack. They might add two numbers together in the case of the add instruction. Then if you want to use things like the memory, right, you have, say, the sload instruction, and this will read a value from a certain storage address, which is reading from this storage here. So you can still get that using the opcodes, but it's not using the stack. And in the debugger, you can see the state of each of those storage areas, storage memory stack, and you can see what the opcode does to it as well. So you can kind of trace what you go through. And if you're just doing day-to-day development, you're not worried about the underlying details. You can just set breakpoints and jump through them and inspect variables and things like that. And finally, we talked about events. We've already discussed them before, obviously, but we talked a little bit about how they look under the hood. So we have an event which is logged into the Ethereum node. It has searchable topics, which are 32 bytes long. The first topic is always the name of the event, hashed. Then you can have 3 optional topics which you want to search by. Then any other information that we want to include in the event gets added to the data, which goes after the topics and isn't searchable. So you can read it if you're always listening, but if you miss it or you want to look back 10 years, you can't go back and search by the data. You can only do that by the topics. So are there any questions on what we've covered today? Awesome.